Welcome. Today we're going to talk about the second derivative and what it means and how you use it to help determine local mins and maxes. So the second derivative helps determine something called concavity. Concavity is a form of kind of curvature. It's not formally curvature in a more three-dimensional sense. It's a curviness of lines. So this is straight. That's a function that has a negative first derivative. This is something with a negative second derivative. So notice the difference. This is always going down. This one goes up and down. It doesn't have to do with the first derivative being positive, negative, whatever. It has to do with the second derivative, where the slope changes from positive, slowly changing down towards negative. So any part of this graph, this part, whatever, is concave down, so it has a second derivative that's negative. Now formally, what does that mean? If the second derivative is negative, that means the function's concave down. Conversely, of course, if the second derivative is positive, that means the function's concave up. What if it's zero or doesn't exist? We're not going to worry about that right now. But there's more to it than literally this, because when you're talking about a function that's increasing, everybody knows what increasing means. It means it's getting bigger. Concave up, what does that mean? The best way to think about it is the classic function of y equals x squared. Because what's its second derivative? Its first derivative is what? 2x. Its second derivative is 2. It's positive. This is a concave up function. It's everywhere concave up. And what does it look like? It looks like this. That's concave up. This kind of derivative is negative. It's getting less negative. It's getting 0, positive, positive, very positive, very positive. As you move along, the derivative is getting more and more in the positive direction. Concave down looks like this. Now there's an easier way to remember this if you like words. There are mnemonics for a whole bunch of things. What I think of is concave up is a cup. Concave up. Concave down is I can't do the same thing, but I'll say frown. See? It's a frown. This is a cup, that's a frown. Concave up, concave down. Now, this is useful not just in knowing how the shape of the graph looks, but it's also useful in finding mins and maxes. Because look at this thing. Where is there a min or a max? Well, there's a min right down there. There's no max. Right here, there's a max and no min. So concavity affects whether you have mins and maxes. And that's what the second derivative test is about. Just like the first derivative test, the first thing you do is find the critical points. Exactly as before. There's no changes. Then, the difference is now instead of finding a number line and plugging things in, we're going to plug them into the second derivative. So we find the second derivative, then we take all these critical points and plug them in. If the second derivative at that critical point is positive, that means we have this kind of shape, we have a local min. If the second derivative is negative, we have this shape, we have a local max. That's the only critical point on that whole graph. It may seem contradictory. Greater than 0 means local min, less than 0 means local max. Now, what about if there's a 0 or does not exist? It'd be great if that meant there is no max or min. Unfortunately, it means we don't know. The second derivative test is incomplete. It can't quite do everything. If you get a second derivative of 0, all that tells us is we're not sure, we better do something else. On the other hand, it's a lot easier for some kind of functions to take the second derivative than it is to make a number line. Let's do an example using the second derivative to find out where there are mins and maxes on this. So here's our function, and the first thing we do is find the critical points. Actually, I'll have you do the whole second derivative test here if you can. Okay, so let's try that. This first derivative is going to be, this is a product, so it's the derivative of the first times the second, plus the derivative of the second, that's a chain rule, times the first. And because I'm going to ultimately have to take the second derivative of this, or the derivative of this one, I want to factor things out. So I've got e to the minus x in there. I've got 3x squared minus x cubed. I can factor that more, but I don't really need to. I'm not going to need it yet, but I might as well just take the second derivative. So I'll do that right now. The second derivative is going to be derivative of the first one times the second plus derivative of the second times the first. And again, factoring things, I've got e to the minus x. What do I have? Minus, minus, I've got an x cubed. Minus 3x squared, minus 3x, I got minus 6x squared plus 6x. Okay, but now back here, I still have to find my critical points. The critical points are always coming from the first derivative. Even if you're doing the second derivative test, find the critical points from the first derivative, where this is 0 or doesn't exist. And just like almost every other function we've done, that does not exist aren't going to be happening. Only those equal zeros. If you've got a quotient, does not exist is relevant because you look where the bottom is 0. But we don't. So I've got e to the minus x times 3x squared minus x cubed equals 0. That means this first piece could be 0, or the second piece could be 0. This first one, e to the stuff. Remember, e to the stuff is always positive. Never 0. That's a false answer. Or rather, there's no solution in there. What about this one? I can factor x squared, 3 minus x is 0. What do I get? X could be 0, or x could equal 3. Those are the two spots. I need to now see what to do by plugging them into the second derivative. I don't need to know the value of the second derivative. I just need to know if it's positive or negative. Plug 0 in. E to the minus, well, it doesn't matter. E to the anything is positive. All I care about is positive or negative. 0 minus 0 minus, uh-oh, this one's 0. So we don't know if it's a max or a min or a not. How about here? 3. That's positive still. 3 times 3 times 3, it's 27. Minus 3 times 3 times 6, that's 54. Plus 6 times 3 is 18. That's negative. So this is a local max. Now, here's an issue with whether or not this one is a min or a max. We're going to have to reason it out because the second derivative test did not tell us. So take a look at this original function. Look at where it's positive and negative. It turns out we can do this relatively easily for this function. When x is positive, this is all positive. When x is negative, we have negative, 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 that makes negative. Times positive, it's still negative. So beforehand it's negative, afterwards the function's positive. It's getting bigger all along. This is neither. It turns out this one is neither. A graphical analysis or a reasoning saves us. The second derivative does not tell us, but we can figure it out. So there's one local max and that one's neither. Till next time, this is Dr. J.